This started in here.
I thought about taking ethnic conflict and global perspective. The teachers really
Let's smack Jacob and make him put his computer on.
Okay, yeah, I'll do that.
He's got their computer out.
I can shut my computer down.
No technology in the classroom?
Yeah.
Then why do you have the camera here?
Oh.
Yeah, you're like that kid in my PhD in one other class when I said, put your phone down, he's like, make me.
Whoa.
Yeah.
That's bold.
Did you?
Yes.
You should
I
keep him out of
affected
class.
Christine Collin has a funny anecdote about that. She said that, never mind, I'm not going to say that.
No, I'm interested. You already started something. Yeah.
Huh?
I'm interested in how you ate.
She claims I showed him my biceps, but really I walked up to the back. He's sitting in the very back room. I walked up to the back room and I was like, it says the syllabus and I can kick you out and give you a 0 if you don't put your phone away. Put your phone away. It was actually his computer, but anyway, it doesn't matter. Okay, so I think we're all here. Okay, so it seems like technology is in our corner today. And so I have the privilege of introducing my graduate student, Casey, who has been working with me for the last 3 years solid. He did a senior design with me, and he's been working 2 years on his master's. He took particle physics as a sophomore, and GR as a junior, and so he kind of came into his senior year.
Ready to rock.
Ready to rock, yeah. And he's been doing a lot of really crazy stuff since then, and a lot of very mathematical stuff. So his thesis topic is actually really nicely tied into what we've been doing recently. I've taught you a lot about special relativity in this class in sort of a sophisticated version, and that directly plays into what Casey's been working on. But I've also taught you a lot about gauge theory, how the standard model forces are understood from gauge theory. And what Casey's basically going to do is fill you in on the missing piece. What's the story we're grabbing? So that I will let Casey have the flow. And I think that probably the best way to do this is if you have any question at any point, ask Casey during the talk. Okay? So if you're confused, probably everybody's confused. So he can clarify things on the board. And so let's just have fun.
I'm Casey. So the title of our talk is Building a Connection Through Obstruction. We're going to try to relate gauge gravity to string theory, but we'll see that near the end. Really, we're going to talk mostly about gauge theories and their mathematical formulations. Just a quick outline, we'll do some introductory material. So we'll talk about some history of gauge theory, where it started. We'll move into a little bit of the functional approach. This is what you guys have been doing in this class. You were writing down action integrals and you were localizing symmetries. So we'll review that briefly, but then we'll jump into just a couple words on general relativity. If you haven't taken the class, I know some of you have taken the general relativity class. There's one. For you, those people, you'll be fine. This slide's really for anyone who hasn't taken GR and just needs to know 1 or 2 words about what world it is, because that's going to be important. If we're going to try to gauge gravity, we might as well know what we're working with. We'll do a little bit of history on gauge theories of gravity, just where it started and what approach it started in. It actually started from the action integral, just like every other symmetry group, and it seems like a natural choice. Then we'll go into the more complicated topics and explain the underpinnings of these theories, which are built on fiber bundles. So we'll talk about internal symmetry groups. So that's going to be like what we've been talking about in this class. So like the electromagnetic interaction. And then we will talk about external symmetry groups, and that's the symmetry groups that we're interested in for general relativity. We're working with like space-time translations, and well, those are external. So then we'll talk a little bit about topological obstructions. That part will probably get to very, very last. Won't spend as much time on it. And we'll talk a little bit about the case of what I think to be the best gauge realization of gravitation. We'll do some conclusions, but let's get started. So, a little bit of history. It was actually in 1929 that Hermann Weyl gauged the local Lorentz invariance of a Dirac action. He was the first one to do it.
I think you made the U1 symmetry.
What?
You said local Lorentz invariance.
Oh, excuse me. Yeah, yeah. Oh, that's bad. Yeah. No, I meant the U1 symmetry. Yeah, if you gauge U1, you get electromagnetism. Yeah, that was bad. Oops. Keep me honest. Then in 1954, Yang and Mills were studying protons and neutrons, and they worked on a non-abelian generalization of Weil's original gauge approach. They didn't get it right, but they introduced the principle, the idea that we should base our interactions on local invariance, and that stuck. And around the 1960s, Glasgow, Salam, and Weinberg came up with their model of the electron-weak interaction, and you guys have been talking about that in this class, where we work with SU2 left across U1y, and we spontaneously break that down to get our electromagnetic interaction. Following this in the 1970s, Frisch, Gale-Mann, and Lukvoya provided a framework for the strong interactions. This was based on SU3. So, what do I mean by the functional approach? So this is what you guys have been working on in this class. We typically have, I don't know if it's tall enough, but we have some action integral that we're going to work with. Here it's just a complex scalar field. What we'll do then is we need to go through 3 steps. So we're going to do a promotion from a global symmetry to a local symmetry. So we've got our global symmetry here where our parameters do not depend on space-time. And all we're going to do is we're going to promote these guys to be space-time dependent parameters. And in the process, our nice global symmetry will break and we'll have extra terms. And we're going to need to do something to soak up the non-invariance. And I'm sure you guys know what we do next. We're going to introduce a gauge field via a covariant derivative. So we're going to use this derivative now. And if we go through our action and replace every instance of our partial mu with our nabla mu, or del mu, that's a nabla if you don't know that. Nabla. Yeah, we'll go through and we're going to replace with this guy, and we'll actually have a local invariance at this point. The requirement is that when I transform the derivative of the field, it transforms homogenously. So the gauge transformation just pulls out from the derivative term. This is how these fields transformed in the global case. So we wanted to mimic that transformation property for the local case. So it makes sense to impose this condition. And it's in the imposing this condition that we actually figure out what the transformation properties of our gauge field need to be, so that we do have a local invariance. Final step, at this point, we need to introduce a gauge kinetic term. This gauge field we have here, A mu, it represents a background in our theory. So we have to specify that by hand when we go to calculate. So we would like to remove that and have our theory tell us how to calculate the background, the configurations of the gauge field. So we need a gauge kinetic term, so we're going to add a field strength here for our gauge field, and we'll take gauge invariant combinations of that field strength, and that's what we're going to shove into this action up top there, and we'll now have an action that includes both a locally invariant matter Lagrangian, so this piece with our nabla is replaced, and we'll have an extra piece that describes the electromagnetic interaction in this case. So now, since we're talking about general relativity, and we're actually talking about gauging general relativity, let's just say what general relativity is. So it tells us that gravitation is the manifestation of space-time curvature. If you've taken GR, you know what that guy is. If you haven't, this is the Einstein field equations. So you solve this guy, and if you do that, you'll get a metric, and the metric describes space-time. On the right-hand side, we have the matter terms. This is the energy momentum tensor, and on the right-hand side, or the left-hand side, excuse me, we have the curvature terms. So that would be like the Ricci curvature and the Ricci scalar. So we might say, how did we get to this? How did we decide that space-time curvature is gravitation? And really, the thing that we need to focus on is the Einstein equivalence principle. And it says that in small enough regions of space-time, the physics reduces to that of special relativity. So what it's telling us is that we need to work with Riemannian manifolds. And if you don't know what a Riemannian manifold is, that's okay. All you need to think about is it's a blob-like space. Here's my little blob. And in small little regions of this space, it looks just like a flat space. And the way that I've stitched this space together encodes the curvature of the space. So it's a way to generalize flat spaces. So our solutions to the Einstein equations tell us about the curvature of this space. Not too bad. So it might seem a little bit, at the start, like these two theories are very different from one another. That GR might not be able to be written as a gauge theory. But we do have this little idea from the Einstein equivalence principle that's telling us that in small regions of space, we have some local invariance, this Lorentz invariance. So that's kind of telling.
Casey, can you expound on the equivalence principle? Because for people who haven't taken general relativity, I think the idea of it is not completely straightforward, but it's at the core of general relativity. So, the idea of taking a small lab and dropping it off a cliff, what you actually expect to happen.
Sure.
Or I can do it. It doesn't matter. There's not half the people in the room that have taken general relativity, more than half. So
yeah. So I can talk about a lab falling off a cliff. So basically, what it's saying is you can detect gravitational effects in very small regions of space. You have to do something globally, and so this cliff falling off. There are multiple strengths of the Einstein equivalence principle, or the equivalence principle. One of them is called the Einstein equivalence principle, and it's about medium strength. It's medium spicy. There are strong equivalence principles and weak equivalence principles. The weak equivalence principle is essentially that if I were to be in some lab and I am, let's see here, I'm dropping it off a cliff, the gravitational, I can equate the acceleration I can equate the masses of the two systems. Yeah, go for it, tag out. I wasn't quite prepared to expound upon.
that's okay. No. I'm not trying to be mean or anything.
No, that's not what I'm saying.
So you guys know if you're in a lab on a cliff, and you drop or you throw a ball up, or you drop a ball. You drop a ball and the ball drops to the ground. Okay? That's the influence of gravity. You have some gravitational acceleration coming downwards, you drop the ball drops to the ground. Okay? However, if you're in a lab that has been, fortunately or not, thrown off a cliff, and you hold the ball out and drop it, what happens?
Nothing.
What happens?
Nothing.
Nothing, right. The ball just sits in front of you. And the reason is because you're accelerating downwards with an acceleration g that exactly matches the acceleration the ball would have. So what we find is if you have an acceleration yourself, if your frame of reference is accelerating with exactly the acceleration due to g, then the effects of gravity disappear. Right? You hold the ball out and let go, it doesn't drop. This is all from your reference frame. This is a special case of a reference frame. This is not what we normally do in Physics 1, right? In Physics 1, we always use reference frames. Well, in Physics 1, we use inertial reference frames. This is exactly a non-inertial reference frame. Okay? But in this, maybe I'll let Casey answer this one. There's a caveat to being able to do this, and that is that your lab has to be small. So number one has to be small.
Yeah. Otherwise, you'll see the curvature of, say, the Earth. You'll see deviations in the gravitational field.
Yeah.
This is locally the same field everywhere.
Yeah, remember the gravitational field of the Earth is not uniform. It points towards the center of the Earth. So if you did this in a really big lab, and as I've drawn it, that is a really big lab. That's the Earth. And you're trying to get rid of a radially directed thing, gravitation, by just a uniform acceleration. And you can't do that. But by making your lab small enough, the gravitational field is approximately uniform, and you can cancel it with an acceleration. Okay, so that leads to the necessity of these small regions of space and time, and that's then what feeds into this comment about manifolds.
So this version is the weak version. So you can keep going. Oh, that's just what it's called. No, I'm not saying it's weak like it's lame. It's just the weak version. You can keep strengthening these principles. You get to the medium spicy version, and that's our Einstein equivalence principle. Is there anything else you'd like me to say about that? Or is there anything else you'd like me to say?
I don't know. Are there any questions? You guys have to ask questions if you're confused. No point going through this if you're like, I have no idea what's going on. Much like you do in my lectures.
Was that a postulate that he made, just a postulate that he started with, or was there actual math that verified that was the case?
Well, I mean, you can write down like the force equations in our small little region in space-time, kind of make an equivalence between the acceleration and the gravitational field. And so there's some math behind it, but I think at the bottom line, it is a postulate that we have. It's something that Einstein formulated, yes. Anything else? No? Yeah?
How do you draw the line from Einstein equivalence principle to Riemannian manifolds?
Yeah, so Riemannian manifolds are spaces that look locally like flat spaces. So in small regions of the space, there's a mapping tape that realizes that space as a flat space. In our equivalence principle, it says that in small enough regions, it reduces back down to Minkowski space, so special relativity. So Minkowski space is a flat space, and really it's just Euclidean space, but we put a special type of metric on it, and it's that -1, 1, 1, 1, right? And so what this is telling us is that in small enough regions of the space, it should look just like a flat space. And since we know manifolds are just blob-like things that, when I look small enough, it looks like a flat space, it kind of seems like, we should be using this type of mathematical object to model our theories.
Okay.
Yeah.
So, is there I'm seeing what's the difference between this and switching out, instead of having mass, you have charge, having electric field instead of gravitational field. It's this one big ball of charge. What's the difference between using it for that, and what's the difference between this and electric field?
So,
Can you repeat the question?
so he's kind of asking, he's seeing an analogy between a giant sphere of charge and say a small sphere of charge that's just above it, right? Directly analogous to our big Earth and our little lab. And he's asking, what's the difference between that? Why are those two things different, or are they the same? That's a good question. So the U1 symmetry is an internal symmetry. It's an additional factor or number that we have to have. Or how should I say this?
It's the universality of gravity is the answer. If you had a big ball of charge and you dropped your lab off a cliff, why would your lab go towards the charge? Everything accelerates with the same acceleration under gravity, right? You can't say that everything accelerates the same under an electric field because it depends on whether it's charged. It's neutral, it doesn't accelerate at all. It depends on what its charge is, right? The force is QE. So gravity affects everything in an identical way, in a way that no other force does. And that's why you can get rid of all gravitational effects at once. So you just can't do it. It's also associated with what Case is saying, but he's saying it in a more technical way.
Very good. Anything else?
No, go on. Go to the next slide.
Okay, all right.
Let the people on.
Let's see, what was I saying before? Okay, so we got this little idea that in small regions of space, it kind of looks like Minkowski space. We go, okay, that's kind of like what we're saying with the gauge theories. We have local symmetries, so maybe. So the analogy is actually a little bit stronger. So if we take a look at some of the equations we use in both of these theories, we do have global invariance in both cases. Here, this is our Lorentz transformation. And V is some vector. We also have local invariance. So again, in electromagnetic case, we have just a phase transformation. but in the general relativistic case, we have general coordinate transformations. And again, we're going to subject our derivative to the same condition that we did in the electromagnetic gauge theory. We're going to insist that when we transform the derivative of the vector, it transforms homogeneously. So that's good. That's looking similar. We also have a covariant derivative. Here it's a little bit simpler. Here it's a little bit more complicated. That's okay. So this is, you can kind of imagine it as like a gravitational potential, just like this is the electromagnetic potential. This is called the Christoffel symbol. If you've taken GR, you know what that is. If you haven't, you could ask me a question about it. Yeah, we can talk about it. But the main point is that both theories have one of these objects, and they're called a connection. So this is a connection, and so is this. We can talk about that a little bit more. That's more of a question. There's also field strengths in both cases. This field strength, again, is a little bit more complicated, but the symmetry group associated with general relativity is non-abelian. And so essentially what we have is that these terms come from the non-abelian nature of our gauge symmetry. Otherwise, we would just have this term, which is very similar to our electromagnetic case. So, okay, so the equations look kind of similar, so maybe we could do this. And as you might suspect, somebody has. So in 1955, Ryu Utiyama gave to the Lorentz Group. Hopefully you all know what the Lorentz Group is by now, sitting through this class, but it's got 3 boosts and 3 rotations. All right, so he did this from the functional approach. So he started with an action, and he gauged the local Lorentz, or he gauged the Lorentz symmetry, and unfortunately, he didn't have any energy and momentum conservation, so that's not good. We usually like energy and momentum to be conserved. He also introduced what are called local Lorentz frames, and he did so in 2 different instances, and they both had different properties at those times, and so it was inconsistent.
Casey, let me say something
Sure.
to give them context. So when we did the gauge U1 to get electromagnetism, we didn't really say this, but it was part of the whole story. One of the things that comes out of that is the conservation of electric current. So you actually get that the change in charge in the region is equal to the current flowing in and out. That's part of the equation that comes from gauging the U1 to get electromagnetism. So, and charge and current are the sources of the electromagnetic interaction. So when you're trying to get gravitation as a gauge theory, the analogy would be the conservation of energy and momentum, because energy and momentum is the source of gravitational fields. And if you don't get that as part of your theory, that's a bad thing. It's kind of like getting electromagnetism without having conservation of electric charge. It just doesn't make sense.
I don't. You're probably going to go into this more, but what are our local Lorentz rings? Like, can we think of them as?
Yeah. So when you're working with spinners in this class, you have to work with those gamma matrices, right? So the spinners can only be defined in a flat space, in a sense. Otherwise, you have to frame your space. And what you do is you start with your reference frame and you do a transformation to make it look like Minkowski space at that point. And so what you do is you run through the space and put little local Lorentz frames, little Minkowski spaces at each point in the space. And this is called a coframe or a local Lorentz frame.
Okay.
So we need these to be able to work with spinners in our space. But as it turns out, you also need them when you're trying to write down a gauge theory of gravity. They kind of just pop up. Another thing that I should tell you about them is that they're actually, like, you can think of them as the square root of the metric. So if you have a non-trivial coframe and you square it, you essentially get the space-time metric out of it. So they're a way for us to, at each point, move to a local set of coordinates that are Minkowski. So we need them for spinners.
Okay.
So when we do this procedure and we go through and we gauge the symmetry, we have something called the Noether current as a result of it. And the Noether current is what leads us to our conservation laws. And this is exactly what Alex was talking about. He was talking about the conservation of electric charge, and it comes as a result of the Noether current. They're just functional derivatives of the Lagrangian. You guys have actually, I'm sure, calculated this without really thinking about it. It's not that bad. Moving on though, so as a result, the nodal current is what couples to the curvatures of the space. So since we had only rotational degrees of freedom, we ended up with spin angular momentum sourcing our gravitational field. And we know that energy momentum is the source of the gravitational field. That's what Einstein taught us. So that aspect of this theory wasn't that great either. Uchiyama tried, he did a great job, and he got us started, and that was awesome. Additionally, there's another piece that was bad, the connection. So again, this is our gauge field connection. It's assumed to be Riemannian, and I can talk more about that, but that's a subtle point. Now, a couple years later, another smart guy named Kibble came along, and he instead said, okay, well, Uchiyama didn't actually use the full set of symmetries of Minkowski space. He used the Lorentz rotations, but he was actually missing one piece of it. You can also do translations, so space-time translations, so X, Y, Z, and T. So the Minkowski metric is invariant under the Lorentz rotations and the space-time translations. So he thought, okay, well, Uchiyama was missing the translations, perhaps I should put those in as well as the Lorentz rotations, and perhaps that will lead to a more complete theory. And it did. This time we had curvature sourced by energy momentum. That's good. Yeah, that's good. And as a result of that, we had conservation of energy momentum. So that's already off to a great start. We also had something called space-time torsion, and that was sourced by the spin angular momentum. We can talk about space-time torsion if you'd like to. Ask me a question about it. It's kind of a weird concept, but yeah.
Can we talk about that?
Yeah. So glad you asked. So in a sense, it's kind of like. So all right, let me start with this. So for a curvature, what we do is we have some curved space, and we take a vector, and if we parallel transport that vector in a closed circuit around the space, if the vector comes back at a different orientation, then that space is curved. Okay. So now we're going to do the same thing in a space with torsion, but the result instead is that the vector doesn't come back to the same location. So the circuit that I draw doesn't close. So this is kind of like if, imagine we're in a room with torsion, and I'm going to do a closed loop, and I'm going to walk like this, and walk backwards, and walk like this to the right, and I'm going to try to come back to that same spot. Well, actually, I'll end up over here. So the loop doesn't close in a space with torsion. There's another interpretation of it as well. So there are two ways to think about differential geometry. One that's more akin to what Einstein did, but there's another one where you work with what are called homogeneous spaces. And the curvature is a measure of how a flat frame rolls over the surface, and the torsion is a measure of how the frame twists as it moves through a surface. So two different interpretations, but it's just another way to characterize a Riemannian space. And in fact, all Riemannian spaces are characterized by these two curvature terms, torsion and curvature. So in Einstein's original theory, he made the choice of having torsion vanish. So there was no torsion in Einstein's general relativity.
How can you have a closed circuit if you're not going back to the same point?
I know, right? It's not weird. Yeah, it's so you're attempting to make that closed circuit, and you just can't get back to that point.
So it's not that you if you do a loop, you just never can get back to that starting point. Is that?
It's not that you can't ever get back there. It's just your vector doesn't.
If you move like 4 feet to the right and 4
If
feet
you
forward.
follow the same procedure you would to do a closed loop on a torsion-free space, in a space with torsion, it would not get you back to the same place. You can get back to the same place doing something else, but the steps you would take to get back there without torsion do not equate to the steps that would get you back there with torsion. I think another way to think about torsion for you guys, which might be a little more not intuitive, but so you know how whenever we write a metric, we always write it as a symmetric matrix? And remember, the metric is how we combine vectors. Well, imagine if to combine vectors, you had a symmetric matrix plus something which is anti-symmetric. And that together was how you kind of described the geometry of your space. Torsion is kind of like an anti-symmetric part of the geometry.
So is the metric anti-symmetric?
The metric is always symmetric. Torsion is anti-symmetric, and then the whole description is the sum of the two. So it's a more general
Okay.
kind of way of doing it. And in fact, in GR, you guys might remember when we derived the Christoffel connection, one of the conditions on deriving the Christoffel connection was that it was symmetric. And that was equivalent to saying the space is torsion-free.
So your second point saying it's sourced by spin angular momentum. So the first point you said that because it was sourced by energy and momentum, we had energy and momentum conservation. Is that second point also saying that we have spin angular momentum conservation?
Yeah, there's a conservation law associated with the spin angular momentum, and it incorporates the orbital momentum as well.
Okay.
But yeah, we do get conservation once you get through. You can see that afterwards, and we can talk about how you get those. You got another one, yeah?
So,
All right.
was there no spin angular momentum conservation in Uchiyama's?
We did have a conservation law on that one.
Okay.
So what it amounts to is taking functional derivatives of the around you, and you're doing it with respect to the gauge field that you're working on. And so in that case, in Uchiyama's case, we had that because we had a certain sense of transformations of rotations.
Okay.
So yeah, it's a direct consequence of the gauge terms. Okay. Moving on. Unfortunately, in this theory, our coframe that we work with doesn't transform how we would like it to. So our coframe is like a little Minkowski reference frame. And we know that Minkowski reference frames transform as they transform like a vector. So I do one lambda application on my coframe. This is our new frame. This is what we like to have. We don't have it. So, it's a subtle issue, and as a result, the interpretation of what the coframe is in Kibble's theory is left unclear. Now, people have gone and used Poincare gravity, this is what this is called, to calculate black hole stuff, see if it deviates from standard general relativity, and the deviations are very small. You can even set torsion to vanish and then just work with the theory just like you would general relativity and everything's fine. It's just that it's a little unsettling that we have transformation properties that aren't really accounted for. We know that we identify terms by how they transform, so we would really like to have proper transformation laws. It's kind of signaling to us that our theory is incomplete, that we're missing something. Is that a question?
Yes.
I see you're
I was waiting for
ready.
you to finish your thought.
Yeah.
So I know in GR we talked about torsion-free. Is there any phenomena that come out if we talk about curvature-free, like a flat space that has torsion?
Yeah, that's a great question. Yes, we can. So what you get when you write down these theories is you get like a hierarchy of gravitational theories. So at the very tip, or not even at the tip top, but at the top of our square, we have an Einstein space. I'll say that again, Einstein Cartan. So this is a space that has curvature and torsion. I can also, if I'd like to, turn off the torsion, and I can get down to Einstein's case. This would be just standard GR. I could also turn off the curvature. Let's put an R in curvature. I could turn off the curvature and leave on the torsion, and as a result, I get what's called, I'm not going to write it, I'll put W. It's a Weizenbach geometry. So yes, there are geometries that have only torsion and no space-time curvature. And there are ways to kind of hit or miss, right, general relativity as a theory only of torsion rather than curvature. But it's very unclear whether or not this theory is actually equivalent to general relativity. One author has found just like tons of initial value problems that are problems in the initial value setup for solving the equations that it just doesn't seem like this can actually reproduce all of this. In very small regions of space, it seems like they're the same. But since we have these issues with trying to solve these problems globally, it seems like it's not as good as we would like it to be. But yes, yeah, you're absolutely right. And then to complete the story, so this has torsion, this one has curvature. Minkowski space is the vacuum solution of Einstein, the Einstein equations. So here this is flat space, so this is Minkowski space. And this actually goes up, there's more theories up here with even more general things. But for today, we're gonna work in kind of this area. We're not gonna go higher up the chain. There's more and more weirdness that happens. Like, if you've taken GR, then you know that one of the conditions we impose is that the covariant derivative of the metric is 0. So that just means the metric's covariantly constant. If you relax this condition and make it so that this is non-zero, then you go up here. You can keep doing things like that. Yeah. It's called the metricity condition. Yeah.
You said before that like the Einstein equivalent principle was a small space-time chunks.
Yeah. Yeah.
So is that like you mentioned that the W box is similar to relativity when you have small space-time chunks?
Yeah.
Is that any way related to like special relativity?
What do you mean? Can you just expound a little bit?
Like, is the W box torsion component box? Is that similar to special relativity, as in for small space-time, special relativity in GR or equivalent?
Yeah, I see what you're saying. So I think at least. Again, in this theory, there are equivalence principles that you can work with. And essentially, what we're talking about over here is that you can, in a certain set of frames, you can turn off the gravitational field. In a sense, you can do that in these spaces too. Yes, but Minkowski space is genuinely a flat space everywhere, and this space can have deviations from. So this one is non-trivial, and this one truly is a space. But you're right, yeah. We can turn off that gravitational field and in certain small regions of space.
I like the way you avoided saying teleparallel.
It's hard to say, man. So these are actually what this is called is teleparallel gravity. It's just hard to say, man.
I wasn't trying to make you say it.
Oh.
I like the way you didn't say it. Good. He struggles every time he says that. Well, it's just another name for that.
Okay.
Yeah.
Call it
It comes
teleparallel
from,
gravity.
it means distant parallelism. So what it means is that two vectors can be compared very, very far away from one another. This is something you can't do in GR. You have to take this vector and parallel transport it to it. So you have to move it in a way that it's as constant as possible while you move it. In this theory, you genuinely can't compare one vector to another one across the universe. So distant parallelism. But it's hard to say teleparallel, so I'm going to not say that. But okay, so going back to the story then, what we learned from Hibble's approach is that space-time translations are very necessary to getting the correct gauge theory of gravitation. They need to be included. The Noether current of the translations is directly related to the energy momentum tensor. And so if we don't have translations, we don't have energy momentum in the theory. So we need translations. Okay. So this is a little bit of motivation for the research that I did. We can go a little bit quick over this point, since I think the purpose of our talk today is kind of get you into the idea of, yeah, we can try to write general relativity as a gauge theory. But what I did, so what we see is that all of these, as it turns out, all of these gauge theories of gravity, the ones that are viable, are going to include space-time torsion. It just happens. You gotta have torsion. It's a bummer, but you know what? We'll just live with it. We'll try to find a reason why it's there and go on, do science. And as it turns out, we're pretty sure that you need to have extended degrees of freedom, like strings, if you want to write down a consistent quantum theory of gravity. So along with this, the graviton, our quantum-mechanical particle that mediates the gravitational force, is always accompanied by an anti-symmetric particle. So we have this Calvert-Bond anti-symmetric potential field. But it always comes with us. They're buddy-buddy. But we're seeing in the gauge gravity case that we also have buddy-buddy going on between the curvature and the torsion. They're good pals, and they don't go anywhere without one another. So that kind of begs the question, are extended degrees of freedom necessary to consistently write down gauge theories of gravitation? This was really the motivation for what I did in my research. Was that what you were about to ask?
I was going to ask, why do we need the extended degrees of freedom for quantum computing?
Why do you need them?
Yeah, why does it seem like you need them?
Well, as soon as you use
Long
them,
story.
Yeah.
If you got a 30-second version, you could lay it on it.
My 30-second version is that if you use them, you automatically get gravity included in quantum mechanics. It just happens. It pops out, and there's a lot of math associated with it.
It's something we'll actually broach at the end of this course. We'll talk about renormalization of theories, and we'll find that gravitation is a non-renormalizable theory, which implies that it has to be replaced by something more fundamental that is actually renormalizable or finite. And it turns out that string theory is an example of something that works, where our normal field theory approach doesn't. So it's not a simple question to answer. Yeah.
It's got a lot of
And it's not that it's not simple, it's just it's a long answer. It's a good question.
Alrighty, so we'll move on from here and we'll talk about now fiber bundles. So fiber bundles are going to serve as our rigorous mathematical foundation for gauge theories. So what is a fiber bundle? Well, it is a generalization of a Cartesian product. So if you're rusty on your math, I've written this up there for you. A Cartesian product of two spaces x and y is just a tuple of elements of x and elements of y. So I just pair together these elements. So we can think of this as R2, two-dimensional flat space. Is a great example of this. Pick an element of x, pick an element of y, that's an element in your space. All right, you need to know that because what we're going to do in the fiber bundle approach, my tongue got all tongue-tied, we're going to start with some space M, and this could be like one of these manifolds that we've been working with in some y shape.
What's the tuple?
What's the tuple? Oh, it's literally that pairing of elements.
Oh, so
It's literally this.
no, I thought that too. Something different.
It's a grouping of things. Yeah. I know, it's very general. It's no math. It's just the right terminology. So I was using it, sorry, I was being a jargon guy, but yeah, it's all it is. You can have triples and so on and so forth. This is a good question. So we're gonna take a manifold or some space, maybe some topological space, and it could be funny looking, it might gurgle out here. And what we're gonna do is we're gonna say that again. So we're working with these manifolds, topological weird spaces, yada yada. I told you about the fact that we're going to use these local neighborhoods, and in these local neighborhoods, it looks like a flat space. So in everything that I do, I work in these little local neighborhoods. And if you can extend that little local neighborhood to the whole space, and the whole space looks like that flat space, well then it's a trivial space. So here I'm writing this like this because I have in mind that M is some non-trivial space. So it's curved or it's stretched or something weird.
Does the space have to be Riemannian manifold or not?
No.
Are you working with the Riemannian?
Yeah.
If we're working in space-time, does it have to be like small spatially and temporally?
Yes.
Okay.
Yes. So that comes in the Einstein equivalence principle. I chopped off a little bit of it, and it says small regions in small amounts of time.
How small?
That's a great question. It really depends, man.
Arbitrarily.
I can't really give you an answer to that until we know more about what we're doing. Yeah. Small is relative. Yeah, you always have to give something to compare it to. Remember, I'm sure you a lot of professors here have drilled that into you. Nothing's big unless you compare it to something small. And again, nothing's small unless you compare it to something else. So you got to pick something and start comparing.
It's small. Sorry, bad time to be eating. I think you can take the length of their lab. They say your lab is a cube. If you take the length of one side and you form the ratio between it and the scalar curvature, so L over R, as long as that ratio is small, no, sorry, R over L. As long as R over L is small, then you can expand in that. And
How small?
How small, yeah.
Well, no, it's like using a Taylor series. You expand in R over L, and you got to keep as many terms as, you want accuracy in whatever you're calculating. If your space is flat, R is 0, so you don't have to be small at all. The bigger R is, the larger the scalar curvature, the smaller you need to take L. No, I've got this backwards. Anyway, it's a comparison of the length of the lab with the scalar curvature in some way that I'm
I thought about that the same. Okay. But yeah, so we're working with our manifolds. They are kind of goofy spaces and it's kind of crazy. So we're going to look at small neighborhoods. That's where I'm working in. But at every point in our space, what we're going to do is we're going to put a fiber space. So at each point, we're going to just attach a new space and we'll call it F. You can think about this as being literally perpendicular to the space if you'd like to, if that helps. There are conditions on whether or not a vector is parallel to the base or the fiber, and I'll talk about that in a minute because it's actually a more deep idea. When we're in these little local neighborhoods, say I have some point in V and I've picked a point in the fiber here F, and so I'm laying at this little dot here and I want to change my realization of this space from working in this set to working in this set. I need a structure group G, and this is going to be a Lie group, so it's going to be like U1 or U2, so on and so forth. And I'm going to use that guy to transfer over to my other neighborhood. So these are called the transition functions, and they take us from what's called a local trivialization to another local trivialization. So what's a local trivialization? In these small neighborhoods, it's very small, and in those neighborhoods, our space looks approximately like a Cartesian product. You just pick an element in base, pick an element in fiber, and that's all you got to do. So that's what's called a local trivialization. However, neighboring local trivializations don't have to be the same, and you could have a shift in the points that you define in the fiber space. So you use a Lie group to transfer yourself between your different neighborhoods that you work in. If you don't need to use any of these transition functions, that means your space is trivial. So it literally can be written as M cross F. So M Cartesian product F, you pick one element in the base, you pick one element in the fiber, and that's how you can actually write this space.
So are each of these fibers the same or are they different?
All the fibers are diffeomorphic to one another. It's a diffeomorphic is a smooth isomorphism.
Yes, they're the same.
So they're the same. So isomorphism is when you say whether or not two groups are the same.
So if F's are the same, you swap the only thing that would be different is where you are in the base space?
The only thing that can be different is like you have here, say this is one trivialization. I could have another trivialization or instead here.
Oh, okay.
And so I need to wait. I need some elements. And since this is a group, I can use a group element to shift myself down here. These are exactly these transition functions.
Okay.
You can also, in language that you might be more familiar with, you know how we talk about the tangent space? Like if you have space-time and there's a tangent space. Well, if you're on the surface of a sphere, the tangent spaces at each point actually are in different directions. So you can't really write a sphere as a space crossed with a tangent space because it's actually a different tangent space at each point. Those tangent spaces are related by rotations, but they're different at each point. Whereas if you're in flat space, you can write the whole thing as a space times a single copy of the tangent space because it's the same everywhere. It's actually very much related to what he's saying.
Okay, thank you.
So it sounds like if I'm looking at two different local, whatever you're calling.
Trivializations.
Yeah, and you do that closed loop that you've drawn. It makes sense to me that you would have to use a group transformation in the Minkowski spaces. Why is it that you have to have a group transformation change the fiber that you attached?
So one thing I'll say before I answer it is that I'm not actually moving through this loop. The loop was just meant to denote that I use a group element to take me from one.
Yeah. So you're like taking one to the next one.
Yeah.
That's
So I just wanted to clarify.
That's what I mean.
I'm not going through like.
Yeah, you're not
space.
yeah.
I just want to make sure that was clear.
Yeah.
So then repeat the second part of your question then.
So if you're doing a mapping from one local trivialization to the other, why is it that the fiber, that your position in the fiber can change and not just in the Minkowski space? Because it appears to me that the fiber is attached at the same point, and if you're
it's related to what we were just talking about with the sphere and the frames on the sphere. So if I have a sphere, I can have a tangent space to a point in here. So this is literally just a flat plane R2. This one is different from.
I get that, but that's
so now hold on. Almost there. This is a fiber bundle in its own right. It's called the tangent bundle.
Yeah.
Okay, and a vector in this bundle is an element of the fiber. Now, if I were to take this vector and try to move it over here, it's not the same vector. It's been rotated.
Yeah.
So I need to use a group transformation, say like a rotation, to rotate me to the correct orientation in the new fiber space. It's exactly what I'm doing in here with these group elements. Is I'm using the group element to help me facilitate moving around this curved space.
Yes. So, but like if you transform from one local trivialization to the other, where that point represents the same physical point?
The point represents the same physical point in space-time, but you have one copy of it that's mismatched from the other copy, and I just need to find a way to do that rotation. Because you don't have to pick the same value in each copy. I can pick whatever one I want in each trivialization. I just have to make sure I sew them together smoothly. I need to have a transition function take me.
Mark, on the
I
next,
can choose
on the
all
next
flat.
slide, he's actually going to give you a really nice concrete physical example of a non-trivial bundle. I think that might answer your question.
Okay.
Anything else? Okay. The total space that we work with is the collection of all of these fibers with all of these local neighborhoods. So I've just denoted that here with an E or a P. We use P's when we fiber vector spaces, and we use P's when we fiber Lie groups. One's called a vector bundle, one's called a principal bundle. So you'll notice a little bit of an abusive notation. The data that we need to construct our bundle E is a base space, some fiber space, a structure group to help me sew everything together smoothly, and what's called a projection pi. Hold on 1 second, let me show you my pi light. I love this thing. It's just a projection operator, just like you would in flat space. So, if I have a vector in R2, I can project this downwards onto this axis, or I can project it like this onto this axis. So, the projection here just takes us down to the base space. Now, if you look at the data we need for a principal bundle, what we do instead is we switch the fiber space from being some arbitrary space that we'd like to work with to being the same space as the structure group. So at each point in the manifold M, we're going to put a copy of the Lie group G, and we'll use that same group to sew everything together. Principal bundles will be the bundles that we use to construct our gauge groups and our gauge degrees of freedom. So the principal bundles we use for that. The vector bundles, turns out there's an associated vector bundle for every principal bundle. And that's when we get matter fields. That's when we get spinors incorporated and all this other good stuff. However, seeing is believing. So let me show you some spaces that you're familiar with that can be realized as a fiber bundle to try to help facilitate this transition into this really mathy topic, as it is mathy. So the cylinder is a fiber bundle. It's a circle, and for each point in the circle, I fiber over a line segment. So for each point in the circle, I put a line segment. If I put them all together, I make a nice little cylinder. So that one's not too bad. That's actually a rather trivial one. There are some non-trivialities. But another one we could do is the torus. So this would be a circle, and at each point in this circle, I put another circle. That one's kind of easy to see too. Another space that might be a little bit more non-trivial, which it is the Mobius band. We can make this as a fiber bundle too. It's a circle, and at each point of the circle, I put a line segment. However, when I go to sew my neighborhoods together, so maybe I should say a little bit about this. When I have a circle manifold, I need open sets to work in, these open neighborhoods, my little regions of space. And so I would have, say, 2 of them, like that. And so I need something to help me facilitate the translation between 2 realizations. And so what I do, instead of just taking my fiber bundle and gluing it together, I do a twist and then glue it together. The transition function is that twisting operation. And so we get a Mobius band instead. So crucially, the Mobius band in small regions looks just like the cylinder. However, globally, it's very different. We can see that. I mean, here we can actually see it. But in more general spaces, we will need a way to differentiate between fiber bundles. You want to say when one bundle is definitely different from another bundle. And that's going to come up a little bit later. I should probably get going here because, boy, we've already gone through 56 minutes. Another really, really important topic in fiber bundles is what's called a section. Now, a section is a mapping from the base part of our space into the total space. And so what I've done here is I have displayed a curve, gamma. And gamma is just a curve that flows through the metals. Yes?
So in that last slide,
Yeah.
we had the electromagnetic is that U1, is that the fiber bundle?
Yeah, so U1 is the fiber space. Yep. So fiber bundles look locally like that Cartesian product, and that's why I put it like this. So our electromagnetism is locally some base space-time, and at each point in space-time, I also have an element of U1. We could actually go through the example of building electromagnetism as a fiber bundle. Yeah. Depends how much time we have. Probably not much. But at any rate, we do have sections, and they are mappings from the base space into the total space. So here's our curve, gamma. It's displayed in green. It's just a curve running only in the base manifold. What we can use the section to do is to move us from the base manifold into the fiber space. And so there's that. So our section mapping assigns for each point in the base a point in the fiber. And so what I've essentially done is I've taken that curve and I've lifted it up through into the total space. The total space being essentially locally m times g. Now, a very important idea is that a principal fiber bundle is trivial if and only if you can find one of these mappings that takes you from the base into the total space everywhere. You can define this mapping consistently across the entire base space. Now remember that these spaces, we typically work in these local neighborhoods in these spaces. And so we typically work with what's called local sections. So if you can take your local section in one of these little neighborhoods and expand it to the entire space-time, then we have what's called a trivial fiber bundle, and it can literally be written as a Cartesian product. So it's a really big idea for us. Sections in in the vector bundle case will represent matter fields. So the matter that we put in our theory turns out to be sections of vector bundles. Now, we can, of course, so that was my little bit about, yes, we can globally trivialize this space as m times g. Okay, let's see if I'm doing all right here. So, since this is the rigorous mathematical foundation of gauge theories, we might expect or hope that there is a corresponding entity for everything that we did in the functional approach for the fiber bundle approach. And there is definitely a corresponding entity for every item in this list. There is an item in this one. However, for this talk, the most important one of these is the first gauge transformations in the functional approach. So that's just multiplying our matter field by some transformation. Corresponds to what's called a vertical fiber automorphism in our fiber bundle approach. So that's a lot of big words, so let's break that down. So vertical being it only moves us up through the fiber, and automorphism is an isomorphism, so that's our way to tell groups are the same. It's a mapping of a group to itself. Since we're working with these principal fiber bundles, we have group spaces as our fibers, and so we're going to take mapping from our fiber space back into our fiber space. I have a nice slide to help you kind of get your head wrapped around that coming up. But first, I do want to say something about, okay, well, we have these translations between the two stories, but if the other one works, the functional approach works, why would we use the fiber bundle approach? What makes it any better? So one reason would be that when we work in the functional approach, we only get half of the Maxwell equations. We get the ones with source terms. So I've displayed that in the tensor formalism, which everyone in this room actually is comfortable with, which is awesome. On the left and on the right, I've translated it to a more pedestrian vector formalism. What, do you like pedestrian?
The idiot on the street can understand.
Man, I'm talking to everybody on the street. So I just walk up to random people and go, gauge transformation.
Learn about fiber bundles?
You ever learn about fiber bundles? What you know about fiber bundles?
Well, I think you're trying to sell me
One of these. Need some fiber bundles?
You don't want to sell me fiber bundles. I want to go home and rethink your life.
Anyways, so additionally, it's tough to interpret magnetic monopoles or monopoles in general in the functional approach. However, as you might guess, we of course can do this in the fiber bundle approach. Fiber bundles are sufficiently general enough to handle all of these problems, and it'll actually fix a lot of our problems, but first it'll fix the second half of the Maxwell equations. We get these second halves as what's called the Bianchi identity. This is a topological condition on our fiber bundle that tells us topological information. I've written it here in exterior calculus language, so it's even more condensed than this language. And I have translated it to, again, more pedestrian vector formalism that any dude walking down the street probably going to know what vectors are.
Just out of curiosity, if using the fiber bundle approach, is there still a way that you can possibly create magnetic monopoles if we ever define them, or is it not?
In the fiber bundles?
Yeah.
Absolutely. As it turns out, the direct monopole is directly realizable as a U1 bundle over a sphere, S2. So what we've learned from that particular case is that fiber bundles, for us, are a generalization of gauge theory to topologically non-trivial spaces like the sphere. So when you work on these non-trivial spaces, you get odd things like the monopole or other objects. So yes, we can deal with monopoles. So we can talk about that. It's a fun little example to do. You can actually back out the quantization condition of the charge. And it's actually rather simple, just one or two rules. But now we might ask ourselves, what can't fiber bundles do? So focusing on that first aspect of that other slide, the previous slide that said gauge transformations are vertical fiber automorphisms. Unfortunately, what that means for us is that these automorphisms only take our curves up higher through the bundle. So let me show you what that would look like. Here's that same image I showed you before where I had a curve in the base space, and I lifted it into the total bundle using my section mapping, this mapping that takes me from the base into the total space. Now what I can do is I can associate a gauge transformation, some group element in the fiber at each point, and I've displayed that as a red vector pointing up. Then, if we were to have this group transformation act on our curve that's been lifted into the total space, what ends up happening is that that curve gets lifted directly upwards. And as a result, we can use our highlight, and what we find is the curve is exactly the same as it was in the base. So the projection of the even higher lifted curve is the same as the original lifted curve. So what this tells us is that we cannot induce any transformations on the base space. The only thing that we're doing is changing points in the fiber space. Now this is an issue because we had seen that space-time translations were very important to the story, and space-time translations move points. So something's not right with vertical fiber automorphisms. They work great for the internal symmetries. We're going to need something more general if we'd like to handle what's called the external symmetries, the symmetries that act on space-time. And of course, someone's done this. So this is called composite fiber bundles. So in essence, what we're going to do is we're going to work with a principal fiber bundle. And what we're going to do is we're going to imagine that our symmetry group, our fiber space, G, is actually a fiber bundle. So it's like fiber bundle inception. There's two layers of fiber bundles going on. What that means for us is, again, we have two bundles. And if we were to try to look at this, you don't have to worry too much about what these two bundles are. I can explain them a little bit more tonight. What we're going to do is, again, we're going to start with our base manifold. We're going to have open neighborhoods in that space. And we're going to fiber over that space these coset spaces, G mod H. And this kind of looks like just a normal fiber bundle that we've been working with before. It's very familiar. And this would be this bundle E that I have displayed for us up top here. That's how we can think of that bundle. It's like this. Then what we're going to do is we're also going to fiber over each fiber more fibers. So it's like hairy grass. Field, there's a grass, the grass has got hairy lines. And those hairs are going to be the group H. And this is the bundle that I've displayed here, P of E and H. Okay, so now the collection of all of this stuff is the total bundle P. So lots of bundles going on. Okay? But the main point of this is that this is going to work for us for gravitation. So to realize gravitational gauge theory, instead, what we're going to do is we're going to work with this chain of mappings. We're going to have a principal fiber bundle. We can project down to E. We can also project down to M. And I will display that for you in just a second. So what we'll do is there we go. We'll use G as this ISO group. So ISO is the Poincare group. That is the set of the translations and the Lorentz rotations. We'll let H be the Lorentz group. And as it turns out, if you take the Poincare group and essentially divide out the Lorentz rotations, you'll get space-time translations. And so that is our G mod H operation. You can ask me about it, but yeah. The main point of all this is that there are two projections in this case. There's one projection from E, our green fibers, down onto the base space. However, there's another projection from our H fibers onto the green spaces. So, and it's through the combination of these two projections that we're able to induce movement in the base space. It's not as simple as that if I move out in this fiber space here, I move like this here. It's a little more complicated than that. But you can imagine that through these two combinations, we should be able to do something that would resemble translations in the space. And as it turns out, you can. It does work for the translations, and it also takes care of the issue of the coframe that we had initially. In our theory here, in this composite bundle theory, the coframe transforms as we would expect it to. This is a good thing. On top of this, we also have curvature sourced by energy momentum. That's a good thing. We have torsion sourced by spin angular momentum. The jury's still out on that one, but at least it's the same as the other ones, so that's good. We get the right transformation properties. We can interpret the coframe correctly. It is still a connection. It is gravitational potential. However, at the same time, it allows us to interpret it as these local Lorentz frames, these local points in space that look like Minkowski space. Okay, coming up to the end here. Yes, sir.
Would there be any benefit to putting fiber bundles on the fiber bundles they put on the
On the fiber bundles. We had this question during the thesis defense. I haven't thought about it.
Okay.
So if I have a, so in that case, let me go back. In the previous case, we used the Poincare group, and then we quotient out by the Lorentz group. There isn't really too many other subgroups I can use the quotient by. However, if I start with a much larger group, I can take a maximal subgroup and quotient by that, and then of that subgroup, take a maximal subgroup and quotient by that, and I can continue this construction.
Oh.
And so yes, yeah, we could just keep going and going, but I haven't seen any need for it in what I do, so I'm not sure. That would be an interesting thing to just kind of play with.
There's also an interesting aspect of this, which I won't make Casey go into, but if you wanted to describe the Higgs mechanism using fiber bundles, you would have to use this composite bundle structure.
Okay.
Which show how a symmetry breaks to a smaller symmetry.
Oh, okay.
Yeah, as it turns out, these are actually the exact formulas for the Higgs mechanism. So I can give you papers if you feel like you'd like to learn about that. I've got a lot of references for this. Okay, so now we have appropriately written down a gauge theory of gravitation. I haven't showed you too much of this theory because it's rather complicated, and the mathematics is, well, it's complicated. But as it turns out, in this bundle E, we require a global section. We have to have a global section of this G mod H bundle. Let me go back so I can show you that. We have to have a global section that can map us from the base space into the green fibers in order to complete this construction. So there are theorems that guarantee us this section, but it's very interesting to ask what that means topologically. So what we might first do is ask, okay, how can we, let's return to this question, how can we figure out if the Mobius band is different from the cylinder? You know, we can look at it and go, yeah, those are not the same thing. If we were an ant on the surface, we'd have no idea. So we have to figure out a way to differentiate between these two things. So topological invariance will be our way to do that. So topological invariance is a number, and if I do a mapping on it, it's the same number, so it's invariant. So in this case, the Stifel-Whitney classes, this is our W and our W, they're not the same. So for a topological space to be the same as another topological space, you have to have all of the invariants be the same. Otherwise, there's no way this can be the same space. So since we have two different invariants in this case, we can differentiate between the Mobius band and the cylinder. This has some complicated math behind it, so if you'd like to, we'll talk about it after the talk. Another related question, and this is kind of a fun one. I don't know if you've thought about this before, but can you comb the hair on a sphere? Has anybody thought about that? You say no. That's a good answer. You can't.
You can comb it.
What?
You can comb it.
You can run a comb through it.
You can. You can. So you actually can't comb the hair on a sphere. So what it is, it's a theorem. It's called the Hairy Ball theorem, and it says, I know.
I have no singularity.
Go look it up. It's on Wikipedia. It's literally called the Hairy Ball
Yeah,
theorem.
there's always a pole.
And what it says is you can't find an everywhere non-zero global section of the tangent bundle for a sphere. Sphere.
Run a hat.
And so this actually also has a topological underpinning. It turns out that a special characteristic class of the sphere is non-trivial, and as a result, we cannot actually find one of these global sections. And so what this tells us is that topological invariants are obstructions to global structures on the object. I couldn't create a global vector field over this object that was everywhere non-zero. And we can actually say that this is because this characteristic class of the sphere was non-trivial. Okay, so now we're looking for global sections just like this of the sphere for our bundles E and gravitation. So we might ask ourselves, which topological classes are we going to have to investigate so that we can answer whether or not we can find a space to build this complicated composite bundle structure. There's a couple. We need the Stifel-Whitney classes. Those are the W's, 1 through 4. We need the Euler class, that's the E. We have a Plum-Tragen class, we're going to need him too. And what this is doing for us is that characteristic classes are measuring the twisting of our space away from this structure. So it's a measure of how far our fiber bundles are away from this type of mathematical structure. But the more fun aspect of this is to ask, what are these characteristic classes obstructing? So, as I said, the composite gauge theory of gravitation requires all of these to trivialize. The first Stifel-Whitney class is an obstruction of orientability. So this is essentially the notion of being able to define a consistent sense of volume everywhere on your space. So in the case of the cylinder and the Mobius strip, we can't do that on the Mobius strip. We can on the cylinder, but we can't on the Mobius strip. The second one, the second Stifel-Whitney class, is an obstruction to spinors. So if we have a non-trivial second Stifel-Whitney class, you can't actually consistently define spinors globally on your space. So if you want to introduce spinors to your theory, you need to make sure that the space that you're working with has a trivial second Stifel-Whitney class. The third one is a restriction to chiral spinors, but as it turns out, if your space has a trivial second Stifel-Whitney class, it automatically has a trivial third Stifel-Whitney class. So if you can get spinors onto your space, you can get chiral spinors for free. That's good. The fourth, it's been argued recently, is related to the causality of the space. So this is a topic that's really important in general relativity. For the Euler class, this is an obstruction to global sections of the space, so being able to write an everywhere non-zero vector field in our space. But the most exciting of all of these classes is the Plum-Tragen class, which is an obstruction to being able to, that was terrible. It's an obstruction to being able to consistently define strings or extended degrees of freedom in our spaces. Also a lot of math associated with this, but what we've seen here is that in our composite bundle theory, all of these classes run Spanish, and as a result, our composite bundles must be primed to be able to have extended degrees of freedom. And so essentially, extended degrees of freedom are dictating classical space-time ontology. But here's the question we started with. Are extended degrees of freedom necessary to consistently formulate gauge gravity? Yes. But that's besides the point today, so I think we'll stop there.